So thank you, Alberto. So thanks for the organizer for organizing this wonderful meeting and giving me the opportunity to present some work that I've been doing in the past 5 years. So I could have chosen other topics in out-of-equilibrium systems like active matter or non-reciprocal hydrodynamic interactions. If you are interested about these topics, please come and talk to me. But since I thought that there would be a lot of people in the room that would be interested in these single file systems, I chose to talk about it. So I know there are lots of experts in the room, starting from Kiran and Tridib, and also seminal work by Herbert Spohn, Satya, and many other people in the room that have been in the field for longer than me. But still, I want to present 2 areas of research that we did in these one-dimensional classical systems with these 3 people. So Olivier and Aurélien, which are at LPTMC Sorbonne, and Pierre-Élien, which is at Phoenix Sorbonne. So, of course, not all of you are familiar with these systems. So may I recap things that Kiran and Tridib already said. So single file systems are systems of diffusive particles confined to one-dimensional space so that they cannot pass one another. So one strong impact of confinement is the fact that if you look at a given tag particle and you look at its variance, then it will be subdiffusive. So variance scales as square root of time and not as time as in usual diffusive systems. So perhaps less known is the fact that this has an out-of-equilibrium counterpart. If you take one particle and drive it to the right, then the motion would be subballistic, and the displacement which scales as square root of time, which has been called in the past a generalized fluctuation-dissipation relation, if you like. So there was experimental evidence of this anomalous behavior, both at the nanometric scales in porous media and at the micrometric scale in artificial systems of colloids. But what I want to focus on today is this symmetric exclusion process that was already introduced in the past. So that's a paradigmatic model on a discrete line in which particles might hop either to the left or to the right with an exponential clock, an equal probability of jumping on either of these sides, and hardcore exclusion, which means that the particle cannot jump if the arrival site is occupied. So this model has a long history. I won't go into all the results, but like in the 80s, Aratia derived the prefactor to the square root of time. And then Derrida and Gershenfeld in 2009 had the full statistics of the current at the origin. And it was only in 2017 that Kiran and his co-workers found the full probability law for one given particle. I should also mention for people in quantum physics that this has connections with larger issues, and in particular, the collective dynamics of the set can be mapped onto a XXX quantum spin chain, although I don't know what would be the equivalent of the tag particle problem in the quantum setting. So in this talk, I will have 2 parts. The first part, I would like to give some insight about the structure of the problem for one particle at equilibrium, and in particular, can we close the hierarchy of density displacement correlations, which are rather physical, I would say, observables that we uncovered in the problem. And then I would move to an out-of-equilibrium problem, which is if you take one particle, you drive it to the right, how to probe such effects of driven particles. And in this case, I would restrict the discussion to the high density limit. Okay, so let's start for the second, with the first part, sorry. So one red guy in the crowd, which looks like this, actually. So one particle in the symmetric exclusion process. And so I will do again some bibliography and highlight 3 points that will be the 3 subparts of this part. So first, the variance. I told you that it was derived by Aratia, the exact prefactor. And actually, in terms of 2 quantities, so the collective diffusion and structure factor, you can have such expression for any single file system. I will come back to this issue later. Then historically, the second thing that was realized was the full probability law in the dilute limit in 2014 to 2015 in these 3 papers. And the nice thing is that for all of these papers, I think you have at least one person in the room here. And finally, in 2017, Kieran and his co-workers found the full probability law. But what I want to show is what is the underlying structure of the problem and why qualitatively this problem is solvable by looking at density displacement correlations. So, okay, let's consider one type particle that will have a displacement x and the occupations of the sites that can be 0 if a site is occupied and 1 if a site is 1 if it's occupied, 0 if it's empty, of course. So for the type particle, you can show that all cumulants, all moments of the probability laws will be sublinear, so they will scale as square root of the time. This, the counterpart for this is that some correlation between the occupation of the site and the position of the tracer particle will have a non-stationary structure. So this is quite surprising because at like for 2D system at equilibrium, you would expect these things to converge to some stationary value. And you have some rescaling, so that goes, scaling functions that goes as R over the square root of the time. And I want to stress that this is the structural counterpart to the dynamical counterpart on the left. And of course, you can write this as correlation functions. And what I will focus in the following are what is this phi of lambda and this psi of lambda and phi of lambda and rescaled position. And the very nice thing is that starting from the microscopic equations, you can uncover exact boundary equations that take this form, and that's why you want to look at these observables. Of course, the less nice thing is that if you look at the equations in the bulk, then they won't be closed. And so you will have some correlation function, which is the usual hierarchy of correlations that you expect. So our goal has been to find a closed bulk equation. So as I told you, we did this first for the variance. So this turned out to be quite easy since the bulk equation is already closed. So that's actually a very nice way to recover the variance looking at the correlation between occupation and displacement. Okay, I wrote the equations, they are not so important, but you quickly recover the prefactor and also the non-stationary form for this scaling function. And actually, the approach works for arbitrary single file system for any given structure factor and diffusion coefficient. Then the second part of our analysis was to look at the low density limit, so the density going to 0. And for this, we found actually a closure relation, which takes this form with the derivative of the cumulant generating function with respect to its arguments. And you find all the cumulants and also all the correlation functions of the problems, which take this form if you want to look at this graphically with like the RC shape for the first correlation function. And then Aurélien arrived in Paris, and actually looking at order by order, he was able to find a closure relation at arbitrary density. And I will only show you the result, which links the generating function of the tracer displacement to these generalized density profiles. And actually, the solution was uncovered as a Wiener-Hopf integral equation for the generalized density profiles, which show you that this is a good equation to look at. So for people in the room that are not very familiar to these integral differential equations, you can maybe see this as a simple generating function of a simple random walk, where Pn would be the probability that the n first steps at our negative positions ending at some position v, and building the generating function of this will give you the structure of the problem. So, okay, we have analytical expressions for the moments that existed before, and also very good agreement of our correlation functions at orders 1, 2, 3, and more with numerical simulations of the system. And so, okay, you heard Kiran talk, and Trideep actually talk about macroscopic fluctuation theory. You can wonder if there is any link between what I'm talking about and MFT, and actually there is, so I won't go into the details of this fluctuating hydrodynamics, which has been presented before, but basically that's MFT corresponds to looking at the large deviation in time of this fluctuating hydrodynamics. So you've got an optimal path for your density between t equals 0 and t equals t. And what can be shown is that our observable, so the generalized density profile, is actually the macroscopic fluctuation theory solution at large times. And so following these results, which are already like 2 years old, there was some recent development. So one major breakthrough was that Kiran and his co-workers found a solution to the macroscopic equations for the step. And so actually they recovered the Wiener-Hopf equations that we had. Olivier and Aurélien very recently, by some kind of tour de force, derived the fourth cumulant for an arbitrary single phase system in terms of the two quantities that I told you about. And also they showed that these generalized density profiles are useful beyond diffusive systems. So for instance, run-ensemble particles or Levy flights. So what I want to emphasize in this part was that the counterpart to the anomalous dynamics of single phase system is encoded in the non-stationary structure of these generalized density profiles that for which we were able to derive exact equations. So let me now jump to the second part of this talk, which is what happens out of equilibrium at high density. And so here, what I want to look at is one biased intruder with all the other particles being unbiased. So you've got a probability P plus to jump to the right, P minus to jump to the left, but only for this particle. I already told you that the displacement will scale as the square root of the time. So this has been known since the 90s, with some known prefactor. But the questions we wanted to ask were, first, can we write the full probability law at all times, not only not only for the displacement, but for all the moments, and not only at large time, but at all times? Can we obtain the n-time statistics? So I will come back to this issue later. And also, can we compute some 2-point quantities in this system? So if you drag one particle to the right, what happens to another buff particle? So these are the 3 questions on which I will go quite fast. But first, how do we approach this problem? And we approach this problem looking at the high density limit. And what we figured out, or actually what was figured out by Brumelis and Hilhorst in 2D and later on in 1D by Pierre and Olivier, was that at high density, you can actually focus on the motion of the vacancies, the holes in the systems, instead of looking at the motion of the particles. And actually, these vacancies will decouple. And so you will reduce the the quite complicated problem of the motion of a tight particle in the SEP to the case of, to the random walk of a single vacancy, which is something that may be hard to do, but is actually solvable. So, okay, for those who like the math, on the right, you have the cumulant generating functions giving you all the correlations of the problem at high density. And on the left, you've got the Fourier transform of the propagator of the problem with a single vacancy. Okay, so now let's see what kind of results we were able to obtain. So first, we obtained the full statistics at all times for these driven particles, which takes the form of some Bessel functions, which enable you to see the crossover between diffusive behavior at very short time and sub-diffusive behavior at large time, and of course in very good agreement with numerical simulations. I should check that S is the equivalent of G in a previous talk. It's the bias on the particle. And we also obtain, of course, odd cumulants, odd and even cumulants, not only the displacement, but all orders in the probability law. And this was also extended to comb structure and to the lattice. So I told you that I may go to 2-point functions now, so let's do it. Let's look at the red particle, which is a distance L behind the blue particle that is driven. And how does this red particle follow the blue particle? And so the crossover between the regime at short time on which the red particle does not see the blue particle and the regime at long time when it is driven by this particle is actually encoded in these scaling functions that scale as the distance between the particles divided by the square root of time, and as a kind of generalized fluctuation dissipation relation, if you like, you can obtain the cross correlations at any order for the two particles. So this was maybe quite fast, just to give some time to more recent results, which is that we wanted to look at 2-time statistics and n-time statistics, if you like, of the symmetric exclusion process. So, okay, let's take one particle and ask the question: what does the covariance x of T1, x of T2 looks like at for 2 times? So this is known for in the literature by various ways. So first, it is widely believed that the set at the Gaussian order corresponds to an Edwards-Wilkinson interface. Actually, in the dilute limits, the problem was solved by Tridib and Bernard Derrida in 2015. And I actually learned yesterday by Kiran that there was a full proof of this 2-point function, which expects to take this form, which is a fractional Brownian motion. So for Brownian motion, you will have T1 plus T2 minus T1 if you want. So an exponent 1 here, or 1/2 if you like. And here you have an exponent 1/4, Hurst exponent, that gives you this form. So questions that we wanted to ask are: first, what happens for a biased particle? Because usually you look at this only at equilibrium. Then what about higher order, beyond Gaussianity? And I won't have time to talk about this issue, but also what is the dependence of this function on all over, on initial conditions. So of course we restricted ourselves to high density, as I told you. And I think our main result that may be expected from what I said before about the random walk of the vacancy, but still is that all the n-time statistics of this particle is encoded in a very simple Brownian motion. So you should know what Brownian motion is. You start from Z0 at time T0 and end up at Z at time t with some propagator, which is the usual propagator. So you would say, okay, this is a very simple problem. So what I claim is that I will take all the times that I like, T1, T2, Tn, and I will ask my random walk to be at positive coordinates, so Z1, Z2, Z3, Z4, at these times, starting from any given Z0. Okay, and so this is the probability that you see here on the right, and then I will integrate this over negative initial conditions. So why not? And this exactly gives me the large density limit of the endpoint correlation function of the set. And actually, okay, you will ask, okay, what happens if I put a bias? Should I put a bias random walk? So the answer is no, because in the bulk, when you are on the gray particles, then there is no reason your random walk would be biased. The only thing happens when you cross the origin. And actually, you can show that you need to consider the 2 to the power n possibilities, Z1 positive or negative, Z2 positive or negative, etc. And a linear combination of these ones will give you the result. So then I may flash what these results look like. So of course, for the covariance, we recover the fractional Brownian motion I told you about. We can also uncover a different covariance for different initial condition. And we have an explicit expression for the 4-time correlation function that is not so complicated, but that I did not want to write fully on this slide. And maybe more importantly, we have the counterparts for the biased particle. So, okay, let's take a little bit of time to explain this. So the first one is quite expected. You go this average displacement scale as square root of t and is proportional to the bias. The second one is already very interesting, because at s equals 0, you've got a fractional Brownian motion. And when your system is completely biased, then what you find is that this depends only on the smallest time. So I should say that the times are ordered, so T1 is smaller than T2. So and so you kind of interpolate between something which is a fractional Brownian motion and something that does not depend on the second time. And we also have a 3-point and 4-point correlation function. And just to show you the structure, because they are not so complicated, they depend on this function, why not, which is the arctangent of the square root of something. And this something is are some ratios of time increments. Yes, Gregory?
So you derive this equation by integrating or performing explicitly this integral?
Yes, yes. So yes, so something that yes, that I should say, because some people that have not tried it may not understand the problem here, is that integrating a Gaussian, a multidimensional Gaussian on a half space is actually something that is much harder than what you expect, and that actually gives you the non-trivial behavior. So it's actually, okay, if you take 2 times, it means that you have, okay, 3 points, so 3D Gaussian, you integrate it on this half face, and this gives you the fractional Brownian motion, which is some way of obtaining a non-Markovian observable by conditioning on a Markovian observable, which was something that I quite liked.
Obtaining a explicit formula for any n, I guess.
Okay, beyond 4, we don't know how to do this. Probably it's linked to the fact that in the literature, like if you look at Russian books, you can integrate FC of alpha 1 x alpha 2 up to.
Only up to n equal to 3. In general, for an arbitrary Gaussian process with given correlator,
Yeah.
you can do this half space integral only up to n equal to 3.
Yeah. Okay. Here we were able to go up to order 4 because yes. So that's That's why. So I think you should remain to this structure here, which may be recast as other forms. I don't know. Okay. So basically, at high density, the complex behavior of a driven intruder is encoded in the simple dynamics of a diffusive vacancy. And so my conclusion was just that I looked at two different problems using two different approaches that we developed for looking both at equilibrium and out of equilibrium at high density.
Okay, thank you very much. Do you have some other question? So maybe I can start because I have one. So with Shamik and Christophe, we look at the problem of this particle when you have absorbing boundaries.
Yes.
And can you use your, because we were not able to solve the problem straightforward. So are you able to use this Brownian model when you have absorbing boundary condition?
That's actually a very good question. I will try to think about it. Like yeah, most of our work was dedicated to infinite system, but I shall definitely check how this high density limit.
Yes, because
scale.
actually there is an interesting behavior.
Yeah.
Okay. There are other questions?
Thanks, Alexis, for this very nice talk. Do you think there is a chance for having a closure in the bias case for arbitrary density?
That's a very good question. I don't know. It was very much. It was much harder than what we thought. So for the moment, we don't have equations. But one thing that I can say is that actually this whole approach, I usually don't say this like this, but comes from the bias case because it's very natural to, if you look just at the displacement, to correlate it with the density of the bath. And so, of course, at order 1, you can write the equations, which is just normal density in the reference frame and coupled to the displacement. And these equations can be closed, and that's the old solution of Gleb.
But for higher orders, you don't.
Sorry?
For higher orders, you don't.
For higher orders, I don't know.
If you try to apply your technique to the slow bond problem, where you take one bond which is sort of slower than other ones, no tracer particle. No, okay.
No, I haven't looked at this precise program, but thanks for the comments.
Okay, so let's thank Alexis again.